Okay, so let's try to build the shear force and bending moment diagram for this guy. Now, just as a conversation, how many sets of shear force and bending moment equations would you have to write for this problem? Well, you'd have to write one that's good for just this first meter, and a second set for this meter, and a third set for this 4 meter segment, then a fifth set for this little segment, and then a sixth set for here. Did I say 6? I meant 5. 1, 2, 3, 4, 5 sets of equations. That would be a cruel and unusual punishment for the examiner. However, you can draw the shear force and bending moment diagram pretty quickly, so let's do that. So remember, we're going to start this by trying to know things about shear force and bending moment. So the easiest ones to find would be the shear over here on this left side. I didn't label this. I'll just call this A. So we'll do the shear at A. That's the positive shear at A. And the positive shear on the right side, is it up or is it down? It's down. And I'll call that B. So this would be the shear at B. What's the moment at A? 0. What's the moment at B? 0. So we should have our starting points in just a minute for our shear diagram, an ending point, and we already know our starting point for moment and the ending point. So to solve this problem, let's take that concentrated equivalent force and convert it to or distributed force and convert it to a concentrated equivalent force. So it's a rectangle. Base is 4 meters, height is 4. 4 times 4, 16 kilonewtons. And it's in between, it should be halfway through, so the distance should be 2 meters on whichever side we choose. So I'm going to sum moments about one of these points and find a shear, and then sum forces in the x direction and find the remainder. So we'll start by summing moments, and I'm going to sum moments about B. You could sum moments about A if you like. So I'm going to sum moments about B. And looking about B, I've got 1, 2, 3 forces. They're all acting down. So what kind of moment would each of them create about B? They're going to create a positive moment. So the first one's going to be 4 kilonewtons times a distance of 1 meter. And then our concentrated equivalent force, 16 kilonewtons times a distance of 1 meter, 2 meters, and then 2 more is 4. And then this 8 kilonewton force. So we got 1, 2, 6, 7 meters. And then finally we get over to the shear at A. And what kind of moment does that create about B? Positive or negative? Negative. So it'll be the shear at A times the total distance, which is 8. So what is the shear at A? Let's see. 11.5? 15. Well, it's close. 15.5? Yeah, okay. Does that make sense? 8, 4. That seems reasonable. Anybody else get that?
Yeah.
Okay, so 15.5 kilonewtons. So we've got a positive shear at A. And then if we sum the forces in the y direction, make sure that's in equilibrium, and I'll assume up is positive, so my shear force at A is up, my shear force at B is down, so that's negative, and then all my applied forces are down, so that'd be minus 8 kilonewtons, minus 16, the concentrated equivalent, and then minus 4. So the shear at B should be negative. And what should it be? 28, 12.5? Is that right? I just did a quick summation in my head. Okay? Any questions about that? So let's see what the shear force and bending moment diagram is going to look like. So I'll construct a template. There's my left edge and my right edge. From our discussion about the shear force and bending moment equations, we know we've got something going on here. As we go left to right, we're going to pass through that force, so we know something's going to change there about our shear. There and there. And then also I've got another change in load. I'm coming here at 0, and then I get this abrupt change. So I want to look at that interface too. So I've got all these same divisions that we talked about earlier. That'll help keep things in line. And then we'll have our positive x, and there's our positive shear, and all of our values will be kilonewtons. So remember, our basic relationships are that the change in shear is going to be the area under the load curve. And of course, the slope of the shear diagram, given by the derivative, is going to be equal to the load at every point. So we'll start with how much the shear changes. So we're going to start with, what's our shear here at the beginning? It's the shear at A. We calculate that to be 15.5. So the change in shear is the area of the load curve. What's the area of the load curve for the first meter? 0. So we should have no change. And the slope of that curve should be equal to the load. And the load is 0. So we have a 0 slope. So that first 1 meter is constant shear of 15.5. Now as I go underneath or past the load from left to right, my shear should change exactly the amount of the load. And that load is positive or negative? Down is negative. So what's 15.5 minus 8? 7.5? So we get an instantaneous drop from 15.5 to 7.5. And now I'm looking at how it's going to change over the next meter. Well, that change should be the area in the load curve. And what's the area in the load curve in that 1 meter? 0. So it should be no change. And the slope of that line is given by the value of the load. And the load there is 0. So we have a curve with 0 slope. So far it looks like just got like a little set of steps going. Any questions about that? Okay, so let's keep going. So what's the change in shear over this next 4 meter segment? Well, according to this, it's the area under the curve. And what's the area under this part of the curve? What's a rectangular base times height? We already calculated it's 16. Is that a positive change or a negative change? Negative. So what's 7.5 minus 16? What is it? 8.5? Negative. And the slope of that curve is given by the load, and the load is constant, equal to 4, and it's negative slope. So you're going to get a negative slope. It's constant. Okay, so let's go to the next section. We've got a little 1 meter section here where there's no load. And since there's no load, there's no change in the shear. So the shear has to stay constant at 8.5 or negative 8.5. And the shape of this curve in between is given by this slope. The slope is the load, and the load is 0. So 0 slope. Now we encounter another point load. So as we go from left to right, our shear should change exactly that amount, minus 4. So what's 8.5 minus 4? 12.5. So So there's our drop down. And then now what about the last meter? Well, there's no load. No load means no change, so we get to end at negative 12.5. And what do we say the shear at B was? Negative 12.5. And the shape of the curve is the load, and what's the load? 0. So there's your shear diagram. Where's the maximum shear? Where does it occur? Yeah, it's in this first 1 meter of the beam, and it's 15.5. Where is the shear 0? Right there. Well, where is there? So I'm going to call this little distance here x1. I already know this is 1 meter. This is 1 meter. This is 1 meter. This is 1 meter. This whole distance is 4 meters. What's that proportion? Well, this slope is the same. So these are similar triangles. So you can say that 7.5, the height, is to x1 as what? This. It gets a little messy. I don't like to do that. So this is what I like to do. I like to imagine this line going all the way back up here. We know that the change in shear from here to here is the area under the curve. What's the change in shear from here to here? If I wrote the change in shear, this part of the graph, from here to here, what's the change in shear? Well, it starts off at 7.5 and ends up at, so the change is negative 7.5. What's the area under the load curve in the same space? It's this. It's a rectangle. And what's the base of the rectangle? I called it x1. What's the height of the rectangle? 4. Is that a positive area or a negative area? Negative. So it should be 4x1. And you know what? These two things have to be equal, right?
Why is it a negative area?
Because the load is negative.
Negative. Okay.
So now you get 7.5 kilonewtons must be equal to negative 4x1. I think you guys can solve for x1. It's 7.5 divided by 4. What is that? It's less than 2. 1.8 what?
7.5.
That's good enough. Everybody see that? So now, where is the shear 0? Well, it looks like 1 plus 1 plus x1. So that should be at 3.875 meters from A. Okay? Now, why did I stop to do that? Well, when we start looking at the next level, which is the change in moment is equal to the area under the shear diagram, we're going to need to know this distance to calculate the area of that triangle. So if this is 1.875, what's this side over here? 2.125 meters, right? So we've got everything we need. So let's see what the moment diagram is going to look like. So there's our positive x, there's positive moment. All these values will be kilonewton meter. What is the moment at A? It is 0. Do I know the moment anywhere else?
B is 0.
Yeah, B. It's a pin, external pin, so I know that's 0. So at least I know where I'm starting and where I'm going. All right, so let's go over the first 1 meter, just like we did before. We know the change in moment is the area of the shear diagram. What's the area under this part of the shear diagram? What's a rectangle? Base 1 times height 15.5. So it should be 15.5, right? And the slope of the moment diagram, defined by the derivative, is equal to the value of the shear. So what's the value of the shear in the first meter? Well, it's constant, and it's positive or negative? Positive. So here's a constant positive slope. By the way, what's the slope of the moment diagram in the first meter? Well, you go and read the shear value, and it happens to be constant. It happens to be what? 15.5. That's the slope of this line. What's the change in moment over the next meter? Well, it says it's the area of the load curve. The area of the load curve here, I'll kind of double hatch that one so you can see that little bit. What's that area? Base times height, 7.5. So if I take 15.5 and I add 7.5, what do I get? 23. And the slope of that curve is the value of the shear. And you go up there and you look, and the shear is constant. And the slope is smaller than the previous one. So you do, I don't think I drew it quite as well as I should, but that slope is smaller than this slope. So this would have a slope of what? 15.5. This section would have a slope of 7.5, about half. Obviously, I didn't draw it to scale very well. So far, so good? So what do we do over the next segment, which happens to be x1, which happens to be 1.875 meters? Well, again, the change in the moment is the area of the shear diagrams. What's the area of this shear diagram? Right here. It's a triangle. So 1/2 base, which is 1.875, times height, which is 7.5. What's that number? Something a little less than 7.5. 7.03. If you add that to 23, you get 30.03. That's close enough. What's the shape of this curve? Yeah. If you look at the derivative, it says it's the shear, and the shear starts off at 7.5 and gets smaller to 0. So the critical thing here is that the slope here is 0. The slope here is equal to this, so you get this little kind of parabolic section. Yeah?
So, whenever we draw those parabolas, it's hard to show that it's 0 whenever you're drawing it freehand. So is it good practice to draw that straight line across in order to show that it's 0 there, or when we're drawing them?
It's not important. The thing about this one being 0 is when we go to the other segment, you'll see that it starts off at 0 and the slope goes down. So this is going to be a peak. So this point becomes what? A max.
Okay.
So wherever you have 0 shear here, that means the derivative of the moment is equal to 0. And when the derivative is equal to 0, you have a horizontal line, which is either a maximum or a minimum of the graph. So that's important to us because maxes and minimums are critical values. In this case, it's going to be a maximum. So that we already know that this is going to be the maximum moment, right? 30.03. And where's it going to occur? 1 plus 1 plus 1.875 meters from the left. So we know where it's going to happen and what its value is. Did that answer your question, Mr. Hall?
Yes, sir.
I did? Okay, so let's go to the next section, this little piece here, which is 2.125 meters. So the change in moment there is going to be this area of the curve. So whatever 2.125 divided by 2 times that, and you can see it's a negative area. So what's that turn out to be? A little more than 8. So subtract that from 30.03 and what do you get? 21. Now that shape is given by the shear. Let's see what. The shear starts off at 0, so 0 slope, and it gets bigger and bigger and bigger to a negative slope. So that might look something like that. And then what's the change in moment over this meter? Would be this area of the curve. I'll just make that one look a little easier to see. Well, that's a rectangle, base times height, so that's a 1 times negative 8.5, so negative 8.5. What's 21 minus 8.5? 12.5. And the slope here, well, it's constant because the shear is constant, and it's negative, so you'll get something that looks like this. And then, of course, the change in moment here, not of course, but at the last 1 meter, the change in moment is the area of this part of the curve, which you can see is 1 times negative 12, subtract that, 12.5. Subtract that from 12.5, you get 0. It connects. And the slope is equal to the shear, and the shear is constant and negative and a little bit steeper. I tried to draw it so that you can see the slope gets bigger here. This is a bigger slope than that. And there we go. So now I can ask you lots of questions about this one. First of all, where's the maximum moment? Well, it's right there. What's its value? 30.03 kilonewton meters. Don't forget your units. And where does it occur? Well, right there. Where is right there? That's right there. So add all those up. 1 plus 1 plus x1. x1 is 1.875. Then I can ask you things like, what's the shear at, what's the slope of the shear of the moment diagram at x equal 7.5? Which is right here in the middle. What's the slope of the shear of the moment diagram right there? Yeah, you just go up and read the shear diagram. It's negative 8.5. What else can I ask you? We already talked about where the maximum shear is. That was 15.5 at A. I could ask you where the shear is 0. We talked about that. Where the shear is 0 usually indicates you got a maximum or a minimum value. This is more likely an exam problem, or a class that would be an exam problem. So any questions? It only took us 23 minutes to work. Yeah?
I do have another question. It's not, well, it could be this one. So if it was a symmetrical beam and we were writing equations, the equation for the first half and the second half would be the same.
Depends on what you're using for your variable. If you're using x from left to right, they would not be the same.
Okay.
If you wrote the first half x from the left to the right and the second half of x right to the left, they would look exactly the same.
Okay, so.
But you got to be really careful if you start moving your origin around. You have to identify that clearly so I can see it.
Okay, so if we do that, we need to show that it's symmetrical and where the origins are.
If you give me an equation, you have to tell me where the origin of that equation is. It has to be clearly identified. Now, for everybody else, we have not worked a problem like that. I've never shifted the origin. I've always kept it on the far left edge and went to the right. I never changed it. But if you see it and you think you can write it differently and faster, you can, and there's nothing wrong with that. I encourage you to not try that on the exam the first time. I encourage you to maybe work some problems at home where you move the origin around and see that there's an advantage, and that's fine. I just didn't want to muddy the water for you guys. Okay.